Thank you. Thank you for the introduction and invitation. It's really a great honor to be given an opportunity to speak in the Zoominar today. Today, I'll report about some recent developments in the study of arithmetic aspects of symplectic Gromov-Witten theory, focusing on the newly discovered relationship between the so-called quantum Steenrod operations and a much more classical invariant known as the p-curvature of the quantum connection. And by the end of the talk, if I have some time, I also hope to report on some joint work in progress with Shaoyun Bai with applications in representation theory that builds up on this relationship. So let's begin by recalling the quantum Steenrod operations, which are the main characters of this story. So classically, if you fix a prime p and look at mod p coefficient cohomology, then this is not just a ring, it actually carries an extra structure. So these have the cohomology operations known as the Steenrod operations. So there's a geometrically defined map called the total Steenrod power map, which takes a mod p cohomology class and gives you a certain polynomial in these variables t and theta with coefficients in cohomology. And the way this map is defined is you start from some mod p cohomology class, take its p-fold tensor product to get a class in the cohomology of x to the p, and then you pull this back by the diagonal inclusion of x inside x to the p. And these variables, t and theta, they show up as the generators of the group cohomology of the group Z mod p, which acts on this x to the p bicyclic permutation. So they're like Z mod p equivariant parameters. Now, let X be a non-negatively monotone symplectic manifold, so something like a Fano variety or Calabi-Yau variety. And just like how you can use symplectic Gromov-Witten theory to deform the usual ring structure on cohomology to get the quantum cup product, Fukaya defined a certain deformation of these Steenrod operations acting on cohomology. So now these are something that act on mod p quantum cohomology, where we recall that quantum cohomology additively is just a cohomology with coefficients in this Novikov ring, which are generated over Fp by these symbols indexed by degree 2 homology classes. It is somewhat more convenient to repackage this data of the quantum Steenrod operations into a collection of linear operators on mod p cohomology indexed by cohomology classes B. And just like any linear operator that you might want to define on flare theoretic or quantum theoretic invariants, these are defined by starting from some geometrically given basis of quantum cohomology and describing the structure constants of the operator in this basis in terms of counts of some holomorphic curves. So for the quantum Steenrod operators, the relevant curve is a copy of a parametrized P1. So this has one input mark point and one output mark point at the two poles of the P1, and P mark points along the roots of unity, which all carry this instance constraint that they should pass through cycles that are represented by this class B that you started from. So this curve has an obvious Z mod P symmetry given by a discretized version of the loop rotation, so you can rotate this curve. And that Z mod P symmetry is what's responsible for the appearance of these equivariant parameters T and theta in this construction. So let's record some properties of these operations. So they're related to Fukaya's definition of the quantum Steenrod operations by this relation that if you evaluate this operator at the unit class in cohomology in H0, then it would give you the total quantum Steenrod power of B. You can also take the classical limit, which means you specialize all the quantum parameters or the Novikov variables to be equal to 0. And the resulting operator that you get is just given by this linear operator of taking the cup product with a total Steenrod power of B. So this property justifies the name quantum Steenrod operations. You can also specialize the equivariant parameters to be 0, which geometrically corresponds to forgetting this Z mod P symmetry on the domain curve, and the resulting operator just becomes taking the quantum cup product with B P times. And finally, there's the quantum Cartan relation proven by Nicholas Wilkins that says that roughly the composition of two of these quantum Steenrod operators are related, or they correspond to taking the quantum cup product on these classes that you put on the equator. So really a key property of these quantum Steenrod operators is that they're compatible with something called the quantum connection. So quantum connection are again a certain collection of linear operators that act on loop equivariant quantum cohomology. These are indexed by degree 2 cohomology classes, and these are like covariant derivatives. They differentiate in these Novikov, the Q variables with connection matrix given by the quantum product. The way you can think about these operators is that there are certain canonical lifts of the quantum product that you have on the usual quantum cohomology to the loop equivariant quantum cohomology. So the loop equivariant quantum cohomology, it doesn't have naturally a structure of a ring, but it sort of has the next best thing, which is the action of these connection operators. So the theorem of Seidel and Wilkins says that the quantum Steenrod operations commute with the action of this quantum connection. And note that this is some kind of differential equation satisfied by this matrix Q sigma B. So using this relation, one can try to kind of solve for this matrix Q sigma B and try to determine it similar to how you would kind of solve an ODE using formal power series methods. So this strategy, using this covariant constancy relation as a computational tool to bootstrap this differential relation to determine the counts in Q sigma B, that strategy would have actually determined this operator Q sigma B formally if you were working in characteristic 0. But in characteristic P, this actually fails, and the main obstruction is that there are these Novikov monomials corresponding to P divisible degrees. So these things of the form Q to the PA, these have the property that these are non-zero monomials, but if you differentiate in Q, they carry a factor of P, so they become 0. So if you try to run this order by order algorithm to try to determine Q sigma B, the algorithm will actually stop short. And this differential equation doesn't tell you anything about the counts of holomorphic curves that show up in Q sigma B in these degrees that are P divisible. So this leads to a natural question, which is how can one try to fully compute these quantum Steenrod operations, including in these ranges of degrees that possibly support p-fold multiply covered curves, so things that are P divisible. And perhaps a more different way to phrase this question is really what are the information that is stored in these P divisible degrees, or what is the enumerative meaning of the quantum Steenrod operations? So this latter formulation of the question, so this was an open question, and this latter formulation is somewhat an open-ended question as well. And this result is my attempt on answering this question. And the answer surprisingly arrives by studying a particular class of examples coming from representation theory, which are called symplectic resolutions. So we'll consider symplectic resolutions as the target symplectic manifolds of our holomorphic curve equation. And I'll explain more precisely what they are in a moment, but for now, let's just say that these are certain smooth, complex, non-compact Calabi-Yau, in fact, actually holomorphic symplectic manifolds, and they also are equipped with certain Hamiltonian torus actions. A canonical example of this is something like the holomorphic cotangent bundle of P1 together with this Kähler form. And this has a rank 2 torus action on it, where the first circle acts by rotating the base P1 and the other circle acts by rotating the cotangent fibers. So the theorem is that the symplectic resolutions, for symplectic resolutions satisfying a certain mild hypothesis, the quantum Steenrod operators on degree 2 cohomology classes can be identified with an expression that is purely in terms of the quantum connection. And to make sense of this statement, I also need to introduce and work with a certain torus equivariant generalizations of the quantum Steenrod operators, which is this superscript T corresponding to this torus acting on the target symplectic manifold. So this expression on the right-hand side, that is in terms of the quantum connection, that is something called the p-curvature of the quantum connection, which is a fundamental invariant that you can always define if you have a connection in characteristic P. So what is this p-curvature? This p-curvature is similar to the usual curvature, which is the two form. The usual curvature is a two form that measures the failure of the covariant derivative to preserve the structure of Lie bracket on the vector fields. So considering the connection as a map from the derivations or vector fields on the base to the bundle endomorphisms, this measures the failure for that map to preserve the Lie bracket. And p-curvature similarly is a one form that measures the failure of the covariant derivative to preserve the p power structure on vector fields, which only exists in characteristic P. So our key observation is that for the quantum connection, we should consider the p curvature that is of the following form. So it's the thing that you saw on the right-hand side of our equality in the theorem. And observe the following similarity with the total Steenrod power applied to a degree 2 cohomology class. So they have the same form, and this is sort of the key observation in this story. In using this observation, one can easily show that the p curvature of the quantum connection actually satisfies the same properties as these quantum Steenrod operators that I alluded to earlier. So this similarity between the expression and the p curvature and the Steenrod operation is the starting point of this story. So the theorem that I presented this follows from this fundamental observation, and also a sort of a new compatibility relation that I show, that the quantum Steenrod operations actually commute with an additional set of operators, linear operators that act on loop equivariant cohomology in this setting, called the shift operators. So these shift operators are some extra operators that you have if you have a symplectic manifold with Hamiltonian torus actions acting on loop equivariant cohomology. So this lemma, you can think of it as sort of a similar result in vein with the earlier Seidel-Wilkins theorem that says that the quantum Steenrod operators commute with a quantum connection. I'm saying that these Steenrod operators also commute with these extra shift operators, which form a difference connection, not a differential connection. And maybe that's all I want to say about the proof itself. But again, the upshot is that the quantum Steenrod operators and p-curvature, quantum Steenrod operators on degree 2 cohomology classes, and p-curvature in the setting of symplectic resolutions, they can be identified. And from the perspective of symplectic topology, this gives you the first full computation of quantum Steenrod operations that work in all degrees, including these degrees supporting p-fold multiply covered curves. And also from the side of representation theory, or from the side of the connection, this gives you a direct one-shot moduli space description of what this p-curvature should be. So this is sort of the two interpretations that you can give to this result. So building on this result, one can formulate this conjecture that this equivalence between quantum Steenrod operations and p-curvature are actually a more universal phenomenon that goes beyond the symplectic resolutions case, because you can define both sides in a broader context that's not only limited to these in case of symplectic resolutions. So this conjecture is a subject of several ongoing work, and I would like to briefly survey what people are working on. So first of all, as Pomerleano announced in the Zoominar a couple of weeks ago, there's a forthcoming work of Seidel and Pomerleano that established this equivalence between the two operators for all closed monotone symplectic manifolds, in the case where your cohomology class is the class with the symplectic form, or the C1. And a slightly weaker version of this statement has already found some spectacular applications. So namely, there's this work of Zihong Chen, his recent proof of the unramified exponential type conjecture concerning the formal singularity type of the quantum connection. It uses at some point, very crucially, some slightly weaker version of the Seidel-Pomerleano theorem, and more observations regarding this quantum key connection, which is related to the quantum connection. So The reason this is so remarkable is that this is a result that is purely in characteristic zero symplectic geometry, but the method goes through characteristic P methods, in particular through this quantum Steenrod equal p-curvature relationship. And finally, there's a forthcoming work of Simon Rezhikov, which shows a version of this theorem for closed Calabi-Yau manifolds. So my examples of symplectic resolutions were non-compact, but there's also some closed CY examples. So even if you don't, so these results, I think, show the following. So even if you don't care about representation theory at all, I think studying symplectic resolutions is still a useful thing because the rich structure that they have and the resulting amenability to computations can really be exploited to shed some new light on more general phenomena in symplectic topology, as this example of quantum Steenrod equal p-curvature relationship really shows. So in the remaining time, I would like to go back to representation theory a little bit and explain a role that these T-equivalent generalizations of the quantum Steenrod operations of symplectic resolutions play in that story. So since I'm low on time, I'll try to be a little bit brief on this. So again, symplectic resolution is a certain smooth holomorphic symplectic manifold. And it's a resolution in the sense that it's a resolution of singularities of this affinization. So this earlier example of T star P1 that I described, you can think of that as a resolution of the quadric cone, A1 surface singularity. So if you blow up the singularity, you get a copy of P exceptional divisor P1, which is like the zero section in this T star P1. So the geometry of symplectic resolutions capture a lot of capture and also generalize a lot of existing structures in geometric representation theory, which is why these are often advertised as the Lie algebras of the 21st century. And there's an influential program in representation theory called the 3D mirror symmetry program, which roughly says that these symplectic resolutions should always come in pairs. And if you're given a group G and a complex representation of group Gn, then from this pair of data with the group and the representation, you can construct two symplectic resolutions that are expected to be duals to each other. So one is called the Higgs branch and the other is called the Coulomb branch. And the 3D mirror symmetry conjecture says, one formulation of it says that the quantum connection or this equivariant quantum D module of the Higgs branch side is isomorphic to a certain D module that you can associate to the Coulomb branch, something called the D module of twisted traces. So using this formulation of 3D mirror symmetry in the joint work in preparation with Shaoyun Bai, we show that this isomorphism between these two D modules in 3D mirror symmetry, they can also be extended to positive characteristic. So this isomorphism, when you work in positive characteristic, intertwines the action of the quantum Steenrod operators on the Higgs side with a certain operators on the Coulomb side related to characteristic P deformation quantizations in representation theory. And I want to say that this proof also goes through this relationship that identifies the quantum Steenrod and P curvature on the Higgs side and some additional computations on the Coulomb side. And this would be the first example, to our knowledge, of the 3D mirror symmetry program that works beyond characteristic zero. So this would be the first positive characteristic example of that story. So that is all I wanted to share for today. And thank you again for this opportunity. It was a great pleasure.
Thank you very much for all this material in this talk, these great results. Are there any questions?
Could you please explain what is this unramified exponential type conjecture?
Yes, so the unramified exponential type conjecture is something that studies the formal singularity type of the quantum T connection. So the quantum T connection is closely related to the quantum connection in this closed monotone case. So you can, in the closed monotone symplectic manifold, you can write down the quantum connection in the C1 direction that I described. And then you can do a certain change of variables to this, and you get a connection now with irregular singularity instead of the usual regular singularity you see for the quantum connection. So it's like quantum connection expanded at q equals infinity. And this ramified exponential type conjecture says that is a statement about the precise description of what the formal singularity type of this irregular singularity of the quantum T connection is. And so and Zihong Chen showed this using some criteria of Kotz in a local monodromy theorem that relates the p-curvature of connections with their singularity types. So, and in January, I think he's also giving, Zihong Chen is also giving a talk in the Zoominar, so you can also hear more about this story from him.
Thank you.
And I think there was a talk by Paul Merliano where he, at the Zoominar, where he explained some of that. Any more questions?